This is a brief tutorial on Hess's Law. So Hess's law of heat summation states that the enthalpy change for the reaction is the same whether it occurs in one step or any series of steps, multiple steps, 10 steps, 20 steps, 2 steps, however many. That works because it's a state function, only considers the initial and the final state. So adding these reactions for steps requires that some rules be followed. First, we want to rearrange the equations given, and if necessary, we're going to shift them so that the reactants or products are on the same side of the reaction as the reaction that we're trying to determine the enthalpy of, and we want to perhaps adjust the stoichiometric coefficients so that the coefficients match so that we get precisely the reaction we're shooting for. If you reverse the equation reactants versus products, that means you'll have to reverse the sign on the delta H. If you multiply the equation by a coefficient to get the stoichiometric coefficients to be the same as in the product equation, we'll have to multiply the delta H by that same coefficient. And you can do both. You can flip it and multiply it. But you don't necessarily have to do both. You can do one or the other, or in some cases you'll just leave it alone. So let's consider this example. If we've got combustion of methane in the A, and the delta H is negative 91.8 kilojoules. A negative delta H implies that it's exothermic, or it releases heat into the surroundings. In reaction B, what it looks like is that we've flipped the reaction from reactants to products, and we've multiplied all the coefficients by 2. So what would be the delta H in that particular case? Well, you'd think you'd flip the reaction, you multiplied it by 2 to get the product equation, and so that means we're going to have to flip the sign on the enthalpy and then multiply it by 2. So we end up multiplying by an equivalent of a negative 2, which gives us a negative 183.6 kilojoules. So that should highlight the rules. Let's look at a couple of real examples. Using Hess's law, let's determine the delta H for reaction 3. So we got iron reacting with oxygen to form an iron 2 oxide with a delta H equal to negative 544 kilojoules. And then the second reaction, we got iron reacting with oxygen to form an iron 3 oxide, delta H negative 1648 kilojoules. And we want to add those together in some way to where we'll equal reaction 3, where we've got the iron 2 oxide plus oxygen reacting to form the iron 3 oxide. So we need to figure out how am I going to rearrange reactions 1 and 2 so that they'll add together to form the third reaction. So what we end up needing to do is to flip the first reaction, and we're going to multiply that reaction by 2, and we'll leave the second one alone. Because what you can see is that the two Fe2O3s is already on the product side in the second reaction, but the FeO is on the opposite side of the reaction and has a coefficient of 2 instead of 4. So we're going to flip that first reaction, and to get the coefficient to match, I'll need to multiply all the coefficients by 2. And you have to multiply all the coefficients by 2 so that the reaction is still balanced. So that means for the enthalpy of that first reaction, I'm going to change the sign, and then I'm going to double it. And then I'll add those two reactions together. So when I do that, notice I flipped that first reaction and multiplied it by 2, and then I've done exactly what I said to the enthalpy. I've changed the sign and doubled it. When I add those two reactions together, anything that's in the same phase, the same substance, same phase on opposite sides of the reaction will cancel. So we can see that those 4 irons cancel on opposite sides of the reaction, and 2 out of the 3 oxygens cancel. So I've got 1 O2 left in that second reaction. But all the ones in the first reaction cancel. Adding that together, we see we get our product reaction 4FeO plus O2 going to 2Fe2O3. And then we add together those two delta H's, the positive 1088 kilojoules and the negative 1648 kilojoules, with a net enthalpy for that reaction being a negative 560 kilojoules. And so that would be the enthalpy of the reaction had we done it in these multiple steps versus doing it in a single step. Get the same answer. Let's look at a different example. So now we want the enthalpy of that fourth reaction. We got 2N2 plus O2 going to form 2N2O. Enthalpy 164.1 kilojoules. Then we got N2 plus O2 going to form 2NO. Delta H there is 180.5 kilojoules. Then we got N2 plus 2O2 going to form 2NO2. 66.4 kilojoules is the standard enthalpy. We want all that to add together to be that fourth reaction, N2O plus NO2 forming 3NO. And we want those three reactions to add together to be that fourth one. So how we're going to solve that is to get the N2O on the right side. We need to flip that first reaction. And the coefficient in that fourth reaction is only a 1, but it's a 2 in reaction 1. So we're going to divide that first reaction by 2 and change the enthalpy correspondingly. We're going to multiply that second reaction by 3/2 to get the coefficient right, because I need 3 NOs on the product side. The NO's on the product side, but it's a 2 coefficient versus a 3 coefficient, so we're going to have to multiply by 3/2. And we're going to flip reaction 3 and divide by 2. Because I need to get that NO2 on the reactant side, and it needs to have a 1 coefficient instead of a 2. And we'll do the corresponding things to each of the enthalpies. So it's reaction 1, I flipped it and divided by 2, so I'm going to divide that 164.1 kilojoules by 2, and I'm going to change the sign. I'll multiply the second reaction's enthalpy by 3/2. And then I'm going to change the sign on the third one, and then we'll end up dividing by 2, and then we'll add all those together. So here are the reactions after I've done all of that. And I flipped and divided by 2, so I changed the sign, divided it by 2. So we get a negative 82.1 kilojoules for the first one. Multiply the second one by 3/2. Notice I got some fractions in there. So we got a 270.8 kilojoules for the second reaction. And then we flipped and divided by 2 again. So we're going to do that same thing to the enthalpy, and we get a negative 33.2 kilojoules. Cancel everything out. The N2s and the O2s all cancel. Notice that there's 1 N2 in the first reaction and a half of N2 in the second reaction, and that'll cancel with the 3/2 N2 on the reactant side, and then the same thing for the oxygen. So what we are left with is N2O, the NO, and the NO2. Add those reactions together and their corresponding enthalpies, and we get N2O plus NO2 reacting to form 3NO with a net standard enthalpy of 155.5 kilojoules. Again, that would be the same as if we'd done it in one step versus all these individual steps. Now, often Hess's Law is done in a little bit more useful form than all those reactions. For any chemical reaction under standard conditions, we get a standard enthalpy change based on the sum of the standard molar enthalpies of formation of the products, and you have to multiply each by the stoichiometric coefficient in the balanced reaction. From that, we'll subtract the corresponding sum for the reactants. And where do I get those standard molar enthalpies of formation? we end up getting them from, say, an appendix of the book or some other source where there's a table of those values. So the net resulting formula will be the delta H standard for the reaction will be the sum of all the standard enthalpies of formation for the products times their coefficients added together minus the sum of all those reactants times their coefficients. Now, the standard molar enthalpy of formation is defined as the enthalpy for the reaction in which 1 mole of any substance is formed from its constituent elements, which means the standard molar enthalpy of formation for an element would be 0. Because if you try to form an element from its constituent elements, you don't have anywhere to go, so it's obviously going to be 0. The symbol for that standard molar enthalpy of formation will be delta H sub F standard, where you've got that little circle superscript means it's under standard conditions. So for example, for MgCl2, we react magnesium plus chlorine to form 1 and only 1 mole of magnesium chloride. When you do that, you end up liberating 641.8 kilojoules. When the energy is written as a product, that means it's exothermic and is releasing that heat to the surroundings. So we'd write our delta H standard of formation as a negative 641.8 kilojoules. Note the coefficient is 1 because you write these standard molar enthalpy of formation. If you write the reaction, you're going to write it form 1 and only 1 mole of the compound, and everything on the reactant side should be an element in its standard state, mind you. So the standard enthalpy of equation is based only on forming 1 mole of product from the constituent elements. These standard molar enthalpies of formation have been determined for many substances and are tabulated and are typically listed in the appendix of your textbook, or there's other sources of chemical data where you could get these values. Standard molar enthalpies of elements in their most stable forms under the standard conditions 298.15 Kelvin and 1 atmosphere of pressure are 0. And that you should know without looking it up. So let's work an example. So if we get the standard molar enthalpy of formation for phosphoric acid is negative 1281 kilojoules per mole, we want to write the equation or reaction for that particular reaction that will yield a delta H formation of negative 1281 kilojoules. When you write that, we're going to write it to form 1 and only 1 mole of phosphoric acid, H3PO4. Doing that will require some fractions for coefficients. You can see we got 3 halves H2 plus 2 O2 plus 1/4 of a mole of P4 will yield our 1 mole of H3PO4. But when you write these reactions, you have to write it using the elements, the hydrogen, the phosphorus, and the oxygen in their naturally occurring forms. That is the form for which the enthalpy of formation is 0 for that particular element, if there's more than one allotrope listed, to form 1 and only 1 mole of the product compound. Remember, 1 and only 1 mole of the product compound will form. Now, if you want to calculate that for any reaction where you don't necessarily form 1 and only 1 mole of product, we can use the delta H equation we used before and calculate the enthalpy change, in this case for H2 reacting with F2 to form HF under standard conditions, 25 degrees Celsius and 1 atmosphere of pressure. So to calculate that, it's going to be products minus reactants times their coefficient. So we'll have 2 times the standard enthalpy for HF minus the quantity of the standard enthalpy of H2 plus the standard enthalpy of F2. Now what we'll have to do is look up the enthalpies of formation of each of those substances and plug it into the equation. So when we do that, we find that the delta H for the HF is negative 271 kilojoules per mole, And for the H2 and the F2, they're 0, like we said before, because they're elements in their naturally occurring state. So then we're just going to take that equation above and we're going to plug these values into it. And it should be pretty straightforward for this particular problem. So we got 2 moles of HF per mole reaction times the negative 271 kilojoules per mole of HF. And I plugged in the coefficients and everything for the elements that are on the reactant side, but you can see their delta H's are 0, as we mentioned before, so that whole term is just going to go away. So we're just focused on the 2 times the negative 271 kilojoules per mole, which the moles of HF will cancel. We'll have kilojoules per mole of reaction, and we'll end up with a negative 542 kilojoules per mole of reaction. So that is the delta H for that particular reaction. Looking at a slightly more complex reaction, we calculate the enthalpy change for this combustion of propane at 25 degrees Celsius and 1 atmosphere pressure. So we've got C3H8 plus 5O2, which we should know that the delta H for that is 0, yielding 3 CO2s plus 4 H2Os. Notice water is a gas phase product here because we have a combustion that's going to liberate a fair amount of heat. So delta H for our reaction will be our products, 3 times the delta H for the CO2 plus 4 times the delta H for the H2O. Then you're going to take that and subtract the enthalpies for the reactants, which will be the delta H of the C3H8 plus 5 times the delta H for the O2. And we want to look up those values in a table, and when you do, you'll find that these are the values. Again, these values may vary a little bit depending on what source your textbook or resource pulled this data from. So sometimes these values do vary a little bit depending on whose book you're reading. But they should be pretty close to what I've listed here. Negative 103.8 kilojoules per mole for propane, 0 for the oxygen, as we mentioned, negative 393.5 for the CO2, and negative 241.8 for the water. So plugging all that in, we're going to have 3 times the negative 393.5, 4 times the negative 241.8, 1 times the negative 103.8, and 5 times the 0. So again, that 0 term kind of goes away. And once you get where you've worked enough of these to where you can see that, you could just omit them when you go to do the calculation because you realize it's going to zero out. So then you work all that out and cancel all the units. And so we're left with kilojoules per mole reaction. We'll add all those up. Adding them up, we've got a negative 2043.9 kilojoules per mole of reaction. And these enthalpies will be for the reactions as they are written. It turns out to be a little bit more useful to just add up the enthalpies from the appendix to get the enthalpy of any reaction instead of trying to add all these reactions together. So this has been a brief tutorial on Hess's Law and adding up enthalpies of reactions.